Hello, everyone, and welcome to the show. This is the GeekNarrator podcast, and I'm your host, Deval Yapte. This is another episode on databases, and today we are going to talk about graph databases and specifically Neo4j. I am joined by Michael from Neo4j, and I'm so excited to have you, Michael, here. We are going to cover why graph databases exist, what is Neo4j, how does it compare with relational model, and the architecture of the database, the scaling model, the internals of the database, and so on. Thanks a lot, Michael, for joining me today. And why don't you start with a little bit of introduction about what you have been doing, how did you end up with graph databases, and a little bit about yourself.
Of course. Thank you, Kavaya, for having me. Yeah, happy to be here on the podcast, and databases are close to my heart. I started out after university doing consulting, especially in the Java space. So I've been using Java since 95, so since the very early days. And busy building a lot of different systems with databases, lots of different databases, Oracle, MySQL, Informix, all the things. And then I also, in the 2000s, I started to attend conferences, contribute to open source projects. And that was really great because at one of these conferences, it was actually a Geek cruise on the Baltic Sea between Norway and Germany. There was a mini conference with a few people, and one of these people was Emil Eifram, the founder of Neo4j. And he did this talk about graph databases and graphs and why this is really important. I found this really intriguing because also some of the issues that we had with relation databases in the past, I could imagine how they could be much easier solved with graph databases. So I got interested and built like first Spring integration for Neo4j. And then in 2010, after Neo4j as a company got founded, I was asked if I want to join the company. So I joined as employee number 10. And since the early days of the startup, I've been at Neo4j for 13 years now. And it's been quite a ride, right? So coming from this really small incubator in the middle in Malmö in a small incubator office, all the way now to a large company with a cloud data platform and all the integrations and all the amazing customers and use cases that we have. And so it's been quite a ride, but it's been always fun. And my areas that I worked on, in the early days, it was everything like from working with customers, working in the kernel, working with the query language, building integrations and so on. But then I also did a lot of work in developer relations, helping all the users of Neo4j being happy and successful with the product, learning from them as well, how they use it, why it's interesting for them, making Neo4j better as part of that. And so building out a DevRel team as well, but still keeping a lot of integration and innovation work as well. So we have something we call Neo4j Labs. So I'm leading still Neo4j Labs. And more recently, I moved to product. So product is actually always been close to my heart, product management. So I'm now working closely with our new CPO, Sudhir, who joined us from Google. And so it's been really great to look at things also from the other side a little bit and see what can we do better in product development as such. So that's a little bit about my history with Neo4j and also in general. Yeah, I'm still really active in the Java space. I'm also Java champion, writing a lot of articles, doing a lot of conference talks. Most recently, lots on Loom virtual threads and these kind of modern features of the JVM and tooling around Java and so on. So it's a great community, both the database space and the Java space. So from that perspective, I'm really happy to be in this field, to be honest.
Thanks a lot for the introduction. And that's quite a vast experience that you have with databases, right? In this show, I typically try to, specifically about databases, I try to talk about a little bit of the history to set up the historical context, like why graph databases exist. And I would love to start for Neo4j as well from the historical context. So I read somewhere that the best model that we can create for the world is a graph, right? So everything in the world exists. They have relations, there are objects and so on. And I totally agree with that. But I'm not sure why did we start with the relational model when we wanted to model more like real world objects, and why graph did not come as the first intuition. So with that, let's set up some historical context.
Question. Yeah. So that's a really great question. And I think if you look at where relational came from originally, so the first relation databases were basically storage for forms. So each table was basically a backend for a single form. So that means the relation table or the relation in mathematical terms is basically backing a single form. And of course, people are working with forms or used to work with forms a lot. They still do, of course. And so this one-to-one storage between table and form was good enough. And then things like connecting tables, joins, were added later to this SQL standard, which you can still see because it feels a little bit bolted on. So it's not like it doesn't feel like a native thing because these kind of foreign keys, and you have to create foreign key constraints, and there's this extra syntax and so on. So that's where we started. And I think SQL has its main advantage because it was always so easy to use, right? So SQL started as structured English query language. Actually, there was a precursor to SQL, which was SEQEL, which was structured English query language, which was much more English than the current SQL, actually. And so that was actually the end user interface for relational databases. So people on their computers that worked with these forms actually were writing SQL queries themselves as an end user, right? And that's where it started. And then, of course, we saw the big developments in relation databases with Sybase, Informix, Oracle, and DB2, and so on. And it became just part of the curriculum, right? Everyone at university learned relation databases as part of the curriculum because it was the go-to. The big 5 databases were all relational, right? So there was actually no choice in some way, right? So there were, of course, other types of databases like object databases and network databases and so on. But they were like more niche players as such. And then, as you all know, after the 2000s, there was this kind of explosion of new data models, right? So like document databases, key value stores, things like DynamoDB, for instance, or Bigtable and others, column stores and so on. And I think people before always made it work with relation databases. So no matter if you ever build applications that your objects or your classes actually represent more like a graph, right? You have entities and they have relationships to each other. So we also talk about the object graph in programming on Java, right? So from that perspective, actually, if you look from the application side, we always worked with graphs in memory when we had our objects. And then we all know there's this object relational impedance mismatch, right? So where you had to basically take your nice, pretty objects and somehow squeeze them in a relational model, right? And we had Hibernate and GPA and all the other things, or other object models like type ORM in JavaScript or so. But we always felt, at least I felt it painfully, often that's a lot of pain, taking my nice objects and squeezing them somehow into this relational databases, how to represent inheritance and composition and relationships and rich relationships and things like that. But it was not painful enough for people, obviously, to do something different, right? Because the libraries helped us more, right? So if you had Hibernate or something like this, then you didn't feel the pain so much. The library took away lots of the pain, right? And so it worked enough in some way, right? And I think that's the reason why there was not enough pressure to look at different data models. But with the NoSQL development and the explosion of new data models, I think this was a great opportunity for rethinking how we store our data. And then you basically say, okay, it's not like we don't put the round peg in the square hole or something like that, but we could actually use the database or the data model that's the best fit for my use case. And for many use cases, relational is completely fine, right? If you just want to store something like forms or products or something like that, one-to-one, and if you have very little variability in your data, then that's a good fit. But if you have high variability, what do? You could use a document database. If you have lots of, for instance, user-generated content with arbitrary data structures, or if you want to have like high performance reads, then you would use a column store, right? So because the column store can optimize reads and analytics and things like that, right? Or if you just have cache like lookups, then you use key value store like Redis or something similar, right? And the same is true for other things, including graph databases, right? And so there were some of the use cases that applications faced that were not a good fit for relational. So for instance, complex hierarchies. If you ever try to express complex hierarchies in a relation database, it's a pain. Or something like pathfinding, or something like resolving access level controls where you have users and groups and permissions and all these kind of things. That's a hard one as well. Or if you do NLP linguistics, if you have multi-dimensional tagging systems or something like that, right? Or recommendations and things like that. So there's a lot of cases where relational is good enough, but then you hit like at some point like boundaries where you say, okay, I really would like to use a relation database. And that's also where Neo4j came from, by the way. So Neo4j actually, like some of the other databases, was not designed in academia or from a research, but Neo4j actually came out of an existing application, which is really interesting, right? So there was in Sweden, where Neo4j originates from, there was a document management, content management system in the 2000s as such, which had a number of interesting aspects. One, it was one of the first software as a service projects or platforms in this space. And it was commercial. So it was not end-user facing, but it was commercial facing. So that meant there was a lot of requirements for security permissions, access management. And if you want to roll this out as a SaaS system, you have to have real-time resolution of permissions, right? So you can't do batch load overnight and then the next day the permissions are updated. You need to, if I change permissions of someone, then I need to see them immediately reflected in the system. And that was one use case. And the other one was multi-language tagging of content, right? So you basically had content, you tagged it with keywords in multiple languages, like all the 27 European languages. And then you wanted to find things that were tagged in German with a synonym in Swedish or English or French or Greek or something like that, right? So you wanted to be able to go through the meaning hierarchies of language and find other expressions basically as that. And so they tried to make it work with relational databases, also had like experts from Oracle and Postgres experts trying to help them, but didn't work out. So they basically started to build out an in-memory system that had more these kind of entities as such, right? Like nodes and relationships as objects. And then basically loaded from the relation database, all the stuff in memory, did all the good operations, the fast operations in memory, and then wrote it back or had to reload it from the relation database. And that's how it started. And then over time, the team basically built more and more database-like functionality into that system, like persistence, like something like for multi-user access, concurrent access, you need something like transaction. And so over time, inside of this real-world application, they built a tiny database, right? And so when the .com bubble burst, the company didn't survive, unfortunately, but they pulled out this graph technology and then worked over several years in turning this prototypical system into a full database system. Basically, that's the history of Neo4j, where basically from a real-world application with the real-world use cases, they were solved in the application and then was pulled out as a system. And when Neo4j actually started, it was a small Java library, right? So it was I think, 300, 400 kilobyte jar file that you could just add to your Java application, and suddenly you had a persistent graph database in your Java application. And that's when we started with Neo4j. That's how our first database in air quotes looked like. And then now it's a large clustering, multi-cloud data platform, right? So it's a really interesting development if you can follow that as such. Yeah, so that's a little bit of the origin story. And the why and how of graph databases, I think it always depends on the use cases, right? So you have certain use cases where document database is a great fit. You have certain use cases where relation database is a great fit. And then you have certain use cases, which you can talk more in later as well, where graph database is actually a perfect fit for that. Yeah. And we often said, we want to encourage people to pick the right tools for the right job and don't do the one size fits all, just squeeze it in somehow. And that's at least our approach to solving people's challenges and problems. Such.
Interesting. That's very interesting to know the historical background and also the journey of Neo4j, how it started with a simple Java library and now how it is like a full-blown database. So pretty good. And I was always confused when I was pretty new to the industry, that it's called relational modeling and relational database management system. But it comes from the relational algebra, where a relation is a table. But it doesn't necessarily talk about relations between objects. And so in a way, it's, I don't know if it's a misnomer bad naming. In some way. Yeah, it's a misnomer. But yeah, the real world, as you explained, in some of the use cases makes more sense in objects and explaining their relationships. And these relationships can have properties and can have multiple relation types and more complex relations. So it does make sense to model. But in a way, our industry has found a workaround with relational databases and modeling the real world into that model. And it works for so many use cases. Like I've worked for so many companies and I've always used a simplified graph model in a relational database. And I guess there is some limit up to which it can work at a sustainable manner, where the cost is not very high, but after a certain time it might shoot. And that's when the graph database would shine. With this, let's define what do we mean by a graph database, because I don't want our viewers to get confused. Should I call my relational database as a graph database if I'm storing graph information there?
That's a really good question. So actually there are two confusions, right? So the first confusion that you already mentioned is relational and the relation in the name. The second confusion is in English, also graph and chart mean the same thing. That's also something that's confusing for English speakers as such.
Yeah.
But in a graph database, I think there's a big difference to relation databases. So the biggest difference is in a relation database, you have one database construct, which is a table, right? And the table has columns, and the table has rows as such. Yeah. And in the graph database, you have actually two main constructs in the database. One is something that we call a node, which stands for an entity. And then the other thing is the relationship. So a relationship is actually not something where I just misuse something like a table as a join table, or I just point a foreign key somewhere. But a relationship is the first-class citizen in a graph database. So you have actually basically two base entities, a node and a relationship. And both have IDs, both can hold arbitrary properties. That's also a big difference between relational databases and graph databases, because graph databases are schema-free, or at least oftentimes schema-optional, so that you have the choice of defining a schema or not. But in many cases, you can just add properties or add attributes as you would add new pieces of data. You don't need to define a schema up front. So you can provide a number of constraints and so on. But in general, it's more flexible on the attribute level. And then the other thing that's really interesting, relationships in a graph database are also like data. So you don't have to predefine these are the only existing relationships that I allow, but as you're adding new types of data or new types of data sources, you can add new relationship as you would add data. So you don't need to change your schema or something like that when you have a new type of relationship, or if suddenly, let's say, there's a new type of attribute that you want to add to your relationship. So for instance, imagine you have certain type of data model and now you want to add confidence to your relationships, right? So you want to say, okay, how confident am I that this relationship exists? Or that, for instance, if it comes from a prediction, from an LLM or ML prediction, right? So then you want to say, I want to also store confidence. So even if you didn't have it before, you can just store an additional attribute called confidence on your relationships. And some might have it, some might not have it. And so it's, from that perspective, it's quite flexible. But that's the main difference, right? So in a graph database, you have really these two core entities. You have nodes, also called vertices in math, and relationships, which are also called edges in graph theory. Actually, that's a good point. It's interesting if you think about relational theory, which is like from the 60s and 70s from Cott, right? Actually, graph theory was invented by Leonhard Euler in the 1700s when he did like the 7 bridges of Königsberg, right? So from the mathematical background, graph theory is actually much older than relational theory, but it took longer. So it took until the 90s, until here Laszlo Barabasi did his network science research. So they basically used the internet to do network research, like where they discovered like how do people communicate, how does behavior spread in networks, how do network structures look like. So that's where network science came from. And then basically it took a while until graph databases became a thing as part of NoSQL. There used to be network databases in the 60s and 70s, which never really took off because they were too complicated to use compared to SQL, right? So because you had to use APIs to work with them. And with SQL, you just wrote SQL, just the language, and used it. But graph databases are like a recurrence of these more flexible network structures, right? So you can do hierarchies, you can do things like long chains, dependency chains. So if you think about supply chains or software dependencies, you can do pathfinding logistics. Social networks have it even in their name, right? So every social network, if you look at how companies interact with each other on markets, or a protein or a complex molecule in biology is also, in chemistry, is also a network of nodes, which are like the atoms, and the relationships are like the bondings as well, right? That's what we touched a little bit in the beginning, but if you look at the real world, there's no such thing as disconnected information or something that's not connected to something else, right? Isolated things don't exist. And it's funny, if you go from the really small, from quantum mechanics, there's a relational quantum mechanics, which basically says attributes of quantum particles are defined by their relationship with other quantum particles, all the way to galaxies. There's even a network of galaxies. So galactic pathways are actually how galaxies in the universe actually form along network structures as well. So you have it really from the quantum world all the way to the universe, that kind of relationship between things define the things. Like we humans are also defined by our relationships, right? If they're all saying, tell me who your friends are and I tell you who you are, or tell me what you read and I tell you who you are, and things like that. So lots of the things in the real world are actually defined through the relationships. And that's their basic graph database, at least from my perspective, do a really good job of representing this rich real world data. Because if you do it with a relational or another database, and oftentimes you basically have to cut it down, right? So you can't really store the full complexity of the data that you have in your real world, but you need to decide, okay, do I want to have a null column that's basically 99% null, and then 1 in 1,000 times is basically a value in there, and then have a really wide table with 200 or 500 columns or something like that? Or do I just leave off the data, which is more rare, right? And then oftentimes the decision is, okay, all the Non-frequent stuff is just left off and ignored, and then you lose a lot of richness from your original information as well. Or if you can't add 20, 30 different relationships to your entity because it's too complex in the relation model, then you leave off perhaps 15 or 20 of them, and then you have only 5 types of relationships left. So your model, all models are just projections of the real world, right? But your model is much less rich when you store it in something like a relation database, and in a graph database, you can keep it much richer than you would do otherwise. Right?
That makes sense. And as you mentioned, I think the key is that relationships are first-class citizens in graph database.
Yes.
And in relational database, there is only one, which is relations. But we try to model to connected components using this foreign key concepts, and we join the tables if you want to connect them. But yeah, that's a nice perspective, and everything in the world is related. There is some connection, as you mentioned. And with this, I want to take a small example, and which will help us move forward and navigate through the understanding of how graph databases work. I want to take an example of an e-commerce application, right? There are products, there are customers who buy those products, they create orders. And so let's take these 3 entities. And this is very commonly modeled in a relational model where you have a customers table, you have a product table, and then you have an orders table. And you map each other, or you connect each other with foreign keys, let's say product ID, order ID, customer ID. And I want to understand how this would be different when we talk about graph databases with an example where, let's say, I'm adding products to the marketplace. So let's say there is a form and I'm filling up that form, and I just enter my product details, and I'm using a graph database because I want to also connect customers and their orders and products and whatnot, and also inventory of the product. So I imagine that there is going to be more and more number of nodes and more number of relations. So I'm using a graph database. I fill up this form. How would the product entity or the object reach the graph database? Take us through a journey from the API to the storage layer.
Yeah. Okay, happy to do that. And this use case is actually quite interesting because if you look at it, it's basically the same use case that you also have for other customer item interactions. So it doesn't matter if you buy a product or watch a video or listen to a song, it's basically all the same structure, right? So you interact with an item. So whatever we talk about now in this or an app store, for instance, if you install apps from an app store. So basically all the things that we talk about now, you can also apply to something like Spotify or Netflix or app stores or other things, which is really interesting because we can look into things like recommendations and so on later, which is quite really interesting. But looking at just what you said, so we have customers, products, orders, and you forgot one thing, which is like the line items, the connection between the order and the product. There's actually an extra table in the relation model, which is the line item table, which you can treat as a join table, basically, or link table, where you have basically order ID and product ID, and then basically the quantity and the unit price, and then the sum, perhaps with a discount or something like that. So the graph model looks similar to the relation model. So you have basically your product node, you have your customer node, and your order node as well. And then whatever you would put in this order line item or join table, you would put on a relationship between order and product. So there would be a relationship between product and order. For instance, say order contains product. And on the contains relationship, you would have something like number of products you order, the item price, if you want to have a copy of the item price, just in case the product price changes later. And then perhaps the multiplied out value or discounts and things like that. And then the customer would have a connection to the order node. So there would be a connection, for instance, saying customer ordered or purchased order or something like that. And then on the purchase relationship, you could have additional information if you wanted to as well, that's pertaining between the customer and the order as such. So that's the overall graph model. So you have these 3 entities and more attributes on these relationships between the entities. But the entities can exist basically on their own, and then you link them up as such. But the relationships can't exist on their own. That's actually an important difference. So in a relation database, I can create a line item table and fill it with data, even if there's not an order and not a product. If there's no foreign key relationship, I can just fill up the table and can guarantee that there's an order or a product on each side of them, can get basically dangling links of some kind. That's something that doesn't exist in the graph database. So every relationship must have a start and end node. I think one big difference, by the way, between relation databases and graph databases is also graph databases are more like entity-centric. So each node, let's say you have different products, like you have I don't know, a TV and a phone and some pair of running shoes or something like that. So each of these products is like an entity or like an instance.
Yeah.
And the product type, or we call it like label, is more something that you add to the instance. So you can say, for instance, this is a product. And you could also add another label which says this is a promoted product. So you would also have product and promoted as two labels. It's more almost like interfaces or roles on the entities. But graph databases care much more about the entities than there's nothing like a table construct as such in the graph database, right? So there's only the data that's in there basically forms the database in the schema. So if you look at the APIs, in the early days of Neo4j, we only had a Java API, right? Which was, of course, nice for Java developers, but not so nice for everyone else, right?
Yeah.
So in 2012, we started to work on a query language for Neo4j, right? So basically that you have then originally we had an HTTP API so that you can basically use any language on the planet to talk HTTP to the server and send the query language over, and then that helps you to read data and write data in the system. The challenge was we started to look at SQL as a query language for graph databases, but we soon felt that it was very cumbersome to express graphs and graph patterns basically in SQL, right? So you always have like entity, join table on these IDs, join and other table on these other IDs, join the next table. So your whole query would be basically massively a large list of joins. And then you wouldn't actually see anymore what are actually my real predicates and what is my select, and because it would just be this massive wall of joins. So they thought it's actually much nicer if you have a query language that can express these kind of visual graph patterns where you have basically like almost circles for your nodes and then arrows for your relationships. And so what we did is actually used ASCII art for that, right? So we called our query language Cypher, and we used actually ASCII art for patterns. So you use round parentheses for nodes, and then a dash greater than sign for relationships, like drawing an arrow in ASCII art. And so with these things, you can actually express these patterns that you would usually draw on a whiteboard, right? Imagine I have a product node on a whiteboard pointing to an order, which points to a customer, for instance, right? So if I think about this on a whiteboard, I can basically take the same and write it in ASCII art in my query language. And then within the parentheses, you can basically put all the information that you want to know about the node, for instance, about it has a product label, it has a certain ID, it has other attributes. And so that's what the query language looks like. And it uses these patterns both for finding data in the database, but also for creating data in the database. So for instance, if I want to create a new node, I would say create, and then just in round parentheses, :product, and then in curly braces, basically all the attributes that I want to pass in as such, like a JSON object, right? And so that's what I would do. So I would, in the simplest way, I would just use HTTP or a driver. So Neo4j has also drivers for JavaScript, Python, Go, .NET, and a number of other languages as well. And you would, similar like you would do in SQL, you would open a database connection to your database, provide your credentials, and then basically send or execute query statement with this piece of Cypher code, which basically says create round parentheses, :product, curly brace, and then you would have something like ID, name, description, and price. And then, of course, because we don't want to have injection, you have like placeholder, $ID, $title, $price. And then you pass them in as a separate parameters map, basically with your client or dictionary in Python or object in JavaScript. And so when it arrives in the database, first of all, do I need to send this query? Is this a write query? Is this a read query? So read queries can be in a cluster distributed to all read servers. Basically, that could be read replicas or parts of the main cluster. And the write queries are basically sent to the quorum of the write nodes in the cluster. So the leader of that statement, if there's not a transaction, it would open a transaction because Neo4j is a fully transactional database. And it would open a transaction, add the data, of course, first to the write-ahead log. And then, so of course, the query engine would pass the query, plan the query, execute the query. And if it has already seen the query before, it would not replan, but it would just use the existing plan. And then call basically kernel API calls that would say create node, set labels, set attributes, and all these kind of kernel API calls will lead to basically creating transaction state in memory, but also writing to the write-ahead log. And then if that's good enough for you, you basically commit your statement, and then with the commit, it finishes the write-ahead log and also adds the data to the store. And then in the store of Neo4j, you have basically a representation of the node. So you have basically a block record entry with the node ID and the labels. and then the properties of the node, either inlined if they're small enough, or sent or stored in a separate file if they're larger, like dynamic strings or things like that are stored separately. So whenever your commit returns, you can be guaranteed that even if the database crashes, it will be recovered from the transaction log and then sent out. And if there's something like CDC configured, then the change data capture would also be triggered, and then the downstream systems would also get updated with this data that's just been written to the database. That's going through from the client all the way to the storage layer and back again.
That's pretty interesting. And I would like to summarize this to validate my understanding as well. Of course, we start with the API, and everything we model it in the form of nodes and relations, and the query language that is called Cypher, if I'm not wrong. And that is also in the form of using like braces and relations for arrows for relations. And that's how you define what you want to create. So in this case, it was product and its attributes. So attributes you can pass in using a parameter map or something. So that is the API layer. So basically, as a user, I am exactly telling what node to create with what parameters. So I'm also defining the parameters of that node. In this case, there's no relation because it's just product creation, right? Or there was a
exactly
relation?
This would be just product creation. Exactly.
Okay. And then once it reaches the API layer, it's a leader based model. It is of course distributed. There's a leader, and then there are some followers that will be used for reads, and for writes we only use the leader. And there will be some consensus. We'll talk about it later. And then it reaches the leader. So it's a leader based architecture. It reaches the leader, and then it will be written to the transaction log for durability. It's pretty standard how it happens in any distributed database. Now, when it gets this data of product, and this is the node, this is the properties, how is it actually stored on the disk? So in relational databases, we use B+ trees to model that and serialize our data. Some databases use LSM trees. What does it look like when it comes to graph database?
So at least for Neo4j, the current storage model looks pretty standard as well. So we have basically record storage. So that means that's something that I missed to say. So Neo4j, of course, has a page cache as well. So basically there's a page-based storage system, and each page basically holds any number of entries of entities. And so there's an entry for a node block, basically. And within the node block, you have basically something like node ID, node labels as fixed data structures. And then you have basically additionally to the node, you have also its properties inline in the same block structure, basically. And then if this node has relationships, these relationships are also sorted and added to the node block as well. So we call this block storage. So that means whenever this page is loaded in memory into the page cache, it's only one CPU cache line or a few CPU cache lines. So we try to be, with the block format, also very CPU friendly in terms of reading, so that it's not basically random access as much. And then only attributes that exceed certain sizes are stored in separate property storage as such.
Yeah.
So Neo4j is not an append-only system. It's basically an in-place update system, right? So you basically have these records, and they can be in use or not in use. So if you delete something, basically the records will be marked as not in use, and then will be reused later. But it's basically fixed-sized records that then have overflow regions. If you exceed certain things, then there will be secondary pages or secondary record blocks as such. So from that perspective, it's probably a little bit like Java memory model also, where you have certain sized regions that are used, and if you get too big, then you get a bigger region, and then it uses that as such. And so we have some other data structures, of course, as well, like indexes and so on, that are standard B trees, so generational B trees basically, and some other trigrams and for text storage and so on. But Neo4j is not like Cassandra, so like an append-only system where you use LSMs, but it's basically an in-place update system as such. But it's pretty standard from that perspective. But what's important to say, many people think also that graph databases or also even Neo4j are sitting on top of a relation database or on top of something else. But actually Neo4j, at least as a native graph database, is really like a full database system, right? So from storage layer over memory management, over transaction system, kernel APIs, query engine, all the way to the client APIs, it's all basically our own database. It's like a full stack database, you could almost say. So it's not sitting on top of another database, because you also see some other graph databases, like you said before. Yeah, you can also just use, why can't I just use a node and relationship table in my relation database and then just basically simulate a graph database on top of it? Yes, you can do it, but you will not get like the best performance and the best attributes out of that as such. And that's something to keep in mind when you look at different graph databases. There are also others, like for instance, memgraph or tigergraph, that are also like full stack databases that have the full implementation as a graph database. And then there are others like, for instance, Cosmos DB, which sits on top of a document database, right? So which has very different characteristics in terms of like operations and costs and so on, because it's basically simulating a graph database on top of another system as such, right? So it comes with a different set of advantages, but also disadvantages, and that's something that you need to take into account.
Makes sense. I think this part is clear. So it's, in a way, it is similar to how relational databases work at storage layer. They also use B-trees for indexes and also page-based storage. Let's create a relation here so we can understand how relations are actually stored. So let's say I create another product where I say the previous product I created, let's give it an ID, let's say 1, and then I create a product ID or product with ID 2, and I say that these two products are related in a way that they have the same manufacturer, for example, right? So this is the relation. So when I persist product 2, how does it look like, and how would the relation be stored?
Okay. First of all, in the model, you would probably not use a relationship to say they have the same manufacturer. You would probably create another manufacturing node or like supplier node and then point both the products to this manufacturer node. But an example for a relationship between two products is actually, are they similar, and how similar are they? So for instance, you would create a like similar product relationship with a similarity score, right? So you could say, I don't know, trainers from Nike and from Adidas are pretty similar products versus something like a trainer and a TV, right? So they are probably not similar. But something like, if you look for Adidas shoes, perhaps you also want to see Nike shoes. So you could use these similarity relationships with a certain aggregation and filters to show someone on the screen, for instance, what are related products. So it's a materialized relationship, a similarity relationship. Basically, the second product you would just create like you created the first product, right? And then, because you can, of course, create nodes and relationships in the same transaction, you basically send a statement as well that says, hey, create this product, like just we did for the first one. But then I also want to find this other product that I want to connect my current product to. So I would, besides this create statement that we just had, we also would use something we call a match statement. Match is find this thing in the database, right? So you would write a match statement, and then you would say basically match curly round parentheses and then colon product and then ID 1, for instance, right? ID and then placeholder, and then you pass in the 1 as a parameter, right? So you have your one product that you just created, the other product that you just found in the database. If you didn't find this database, this product in the database, it would just return nothing. So that means this query would have empty rows, so it would not produce any rows. So that means the next step, meaning the relationship creation, would not happen, right? Because it wouldn't, if it hadn't found the second product, then it would have no results, and then the relationship creation wouldn't happen. And then you can basically just say create, and then you say P1 similar to P2. So you use something we call identifiers or variables for each of the two products. You have P1 is the product you just created, P2 is the product that you found in the database, and then you basically say round parentheses P1, arrow, square brackets, similar to, round parentheses P2, and that would basically create a relationship between the two. If you give the relationship also an attribute like similarity, then you would basically can pass this in again into a JSON curly brace map, or you can also afterwards set the attributes. So for instance, if I run the create statement and I give this similarity relationship a variable like s or something like that, and I can basically also do set s.similarity equals and then parameter that comes in as well, right?
Okay.
That's how you would create a relationship. So you basically really spell out, okay, create this first product, find the second product, create a relationship, and it's all like this ASCII art, which has the big advantage that if you show someone who's not a developer this kind of ASCII art representation of your domain in the queries, they can still read and understand what's happening, which I really like, because that means that all the business people or the people like your PM or your customer, you can actually take them along, and they much longer understand what you're doing. Instead of with relation database, I always had a problem. They were just seeing joins and tables, and they said, okay, you lost me here, and I don't know what you're doing here. Something crazy with SQL. But here, because you have this kind of visual representation of these patterns, that's something that people are really good at recognizing. And so that's a nice side effect of this.
Absolutely.
And then, of course, the other part, it would go through the transaction stack the same way as it did the first time. If it fails for whatever reason, so for instance, if there was like concurrent access or you got a deadlock or something like that, then you would get an error and then your transaction would be rolled back. And then you would basically get notified that your transaction was not successful. But if it's successful, then it's basically committed. And then, of course, in the leader architecture, it would distribute it to the other leaders as part of the quorum. So they have the commit quorum as well, like other databases as well. And then the read replicas or the followers would basically get updated. Or secondaries, they would get updated depending on the configuration and setup. So these would be eventually consistent as such.
Yeah. That makes sense.
Yeah, so that's how you basically, so it's patterns time and again, basically. So from that perspective, it's actually pretty straightforward. But the only difference is, of course, if you create this relationship, then there's not an entry created for a node, but basically the relationship is added to both nodes as an entity as well in a block storage. So the relationship and the attributes are added in the inline block, basically.
That makes sense.
Well, right? So
that makes sense.
Then it's basically stored there.
Yeah, I think I understand the difference here, but I want to make it solid understanding. So I'm from a relational background, right? So I'm trying to make sense of how is it different than storing a reference for a foreign key, which is a primary key for another table or another row, so to say. And how is it different? So where is exactly the performance benefit coming from? Am I not storing the reference again to a different page where the node would exist, or how does that work?
Yeah. So I think the main difference is really in the type of how you find this reference, right? So graph databases are often called, or also use something that's often called index-free adjacency. So that means you find the neighbors that are adjacent to a node without using an index. If you think about relational databases, to find the entries in this other database, in this other table, you need to use an index, either a primary key index or an foreign key index or something like that, or like a multi-value index or so. And in a graph database, what we basically do instead is we point directly to the memory location or to the record ID because we know it's not just a table, but we have really these different types of data structures in the database, right? So we exactly know, okay, if there's a relationship pointing to a node, that's exactly the record ID, right? So it's something that relational databases could do in general as well if they wanted to, but then they have to move away from this generalized table approach, and they would have to have specialized data structures for these kind of things, right? And that's, you don't need to use an index. So in a graph database, the only time that you use an index is when you find the entry points into your query, right? So for instance, if you start with a product ID or with a person customer number or a book ISBN or something like that, or a geospatial lookup or something like that. That's the only time that you use an index in a graph database. And all the other operations in a graph database are basically just following pointers in memory, if you think about it. So they basically navigate almost, it's really just almost, if you imagine like your object graph of a program sitting in your heap, you basically just follow the pointers in memory. And so you don't need to go back always, okay, I need to go to the next step. So I need to go to the index first. I get a result back from an index. Okay, I get the next step. I need to go to the index first and go back to the index. And because indexes also grow quickly with the data volume, that's a problem. And then also the more of these index lookups you have, the more relationships or the more joins you have in your query. This also adds up to the complexity because it has to be done for every, not just once, but for every entry in the path or every row that's produced. Has to do n index lookups, right? So basically, if you have 6 steps, so that means at least 6 or 12, depending if it's a join table or not, 6 or 12 index lookups times the paths that you have basically in there, right? So it explodes pretty much in complexity. And if you basically get, 2 orders of magnitude performance improvement by just following in memory pointers for each of these navigations, that makes a big difference in how this performs at read time. So it's, in the end, graph databases basically trade in some way. What you do, you prematerialize these joins in some way, right? So you don't compute the joins at query time, but you compute the joins at insert time, at the write time. So you prematerialize these joins by having then these memory pointers, and that gives you a little bit higher costs when writing, but you get a massive performance improvement when you're reading the data as such.
That-
So that's the main difference actually, right? And you can do it because you have these two different data structures or data types in the database that actually have really semantic meaning. It's not just yet another table, but it's really, a relationship is really something different than a node in terms of what it entails basically.
Yeah. Before we try to dig deep into the read path, we have covered it in slightly brief. So as you mentioned that instead of joining at the query time, we take a little bit of performance hit on the write, on the insert,
Yeah.
and then we make sure that we have the exact memory address of the relationship where it is stored.
Yeah.
And so I have two questions here. So first one is, since you're storing the memory address directly, is that the reason you use a mutable form of structure?
Yeah.
So that you can't.
So that's, yeah, it definitely helps. Yeah, exactly. Because if you have an append only structure, then you would have to, like similar, like for garbage collection, you would have to re-update all the IDs and all the pointers basically.
Yeah.
And that's why we use the in-place updates, right? So we have some approaches where we work on this basically with a generational approach. So similar like to generational GC, where basically these IDs can be repointed and reallocated and so on. So it becomes more like an append-only thing, especially for like MVs and things like that, where you basically want to have different versions of the data. But yes, in general, that's one of the benefits of using an in-place update structure, that you can, these IDs are internally stable and you can continue to use them without needing to recompute them as such.
That makes sense. But how about the locality of data? Let's say, so with this, I also want to talk a little bit about the partition strategy, like how we are. So let's say the first products get stored on, let's say, a node, which is a leader. And then the next product, if I have defined a relation with product one, for example, is that how it knows I have to store it on the same machine, or it can be stored on a different node as well?
So in principle, it's up to you how you want to partition your data. So we, right now at least, we use basically user or customer indicated sharding approaches, right? So we ourselves basically store the full graph as such. So we have something that we call Fabric for federated querying, basically, where you can basically pull data from different charts say so. But it's basically more I based on, for instance, on an order ID or based on something like click date or geography, I want to send this data to this chart or I want to send it to this chart as such. What we oftentimes do in this partitioning or sharding approach is we keep all the like master data in one place. So all the like the customers, all the products and all the category suppliers and all the other things, we keep this in one place. And then more the transaction data, which means purchases, views, ratings, and things like that gets sharded out, because then you can basically just shard this, for instance, time-based or geography-based. Then you say basically every whatever month or week, we create a new shard for the most recent data, and then we use that. Or we do it by geography, where we say basically by main region, we shard things out like that. But then like the essential core model, which is the product suppliers, the categories and customers are kept together. So they're always efficiently accessed. And then we create something like an proxy entry in the shard that has the transaction data. So you would have a proxy entry for the node or for the product or the customer node in the transaction shard. And then these would actually point to these proxy nodes. So then when you do queries that just basically touch the product or touch the customer, they would still all work. But if you want to then fetch like all the data from the customer or from the product, then you would go to the main shard, which has the master data, to say so, in that. Right. So that's our current approach. We're also looking at some other approaches there. There's a little bit of a challenge because graphs are highly interconnected. And then sharding them becomes like an research and scientific problem, but we don't want to go there. So that's why we try to keep it as simple as possible right now. But we're also exploring other approaches where we can we do basically auto sharding just based on timestamp or something like that, and then use that instead. What's actually interesting is we have oftentimes seen with customers that they can actually use much fewer instances of a graph database than for others. So we had, for instance, Adobe with Behance. They had a Cassandra-based approach where they had lots of Cassandra instances, like 60 or so. But because it was a social graph, right? So it was inherently a graph problem. So they basically had to, what they had to do in Cassandra, they had to basically duplicate a lot of the data for all the different approaches on how they wanted to access and navigate it. So there was a lot of redundant data as such. And then when they moved to Neo4j, they basically had a 3 cluster basically just for high availability. So they didn't need all this compute because the structure for a social network was much more a natural fit. And so all this data duplication was no longer necessary because it was basically a social network of artists and their products. And so that was something that we've actually seen in multiple cases where the usage or resource usage went really down because then you only used what you really needed. And also with the dynamic properties, you don't need space where you don't have properties for attributes for it as well, right? So that was also something that was interesting as such. Yeah, but that's our current approach to sharding, and we use federation more than like auto sharding and such.
That makes sense. So if I understand correctly, basically data locality is a very important property. You want the entire graph for one usage pattern.
For one query, right? So for your, for your pattern.
Exactly. To be on the same machine. Otherwise, it might be complicated. If possible.
Yeah.
But if let's say...
You can still do it. It's like a MapReduce pattern where you basically fan out the queries and then get them back on a compute node, and then you do the aggregation there. But each individual like subgraph, if you want to call it this, should be contained on one machine, right? But each subgraph can be on a different machine, but they should be connected as such, because otherwise you basically add network latency to the graph operations, which is something that you want to avoid.
Such, right? So that's when the data modeling part of it would become extremely crucial, because if you're not modeling it correctly, it might end up on different nodes, and it might be even worse than using a relational database. That makes sense. And when I'm creating these products, I'm also defining a relation. So my intention ideally would be to create the relation which I am going to query on, right? Otherwise, it's a useless relation, right? So I can think of, let's say, oh, two products are related. I am going to store this relation because I'm paying the right cost, because it is updating, it is not using joins and all. But if I don't query on that relation, it's useless, right? It's wasteful.
That's a really interesting question, right? Because it's similar to the question that you ask in data lakes and lake houses, right? So where you basically say, okay, I have all this information and I don't know yet what my use cases will be. So I'd rather store it. And even if I don't touch it, right? So that's actually a thing also in the graph database, because most of the graph queries are local queries, right? So you have some starting point and then you follow some relationships to a certain degree. But all the data that you don't touch, or that you don't access, will never be loaded. So it basically just sits on disk, but it does not get even touched by the system, which then has the advantage that you can store it, but if it's not in the hot data set, it will actually never be loaded as such. So it just sits on disk basically. Of course, it takes disk space, but it will not take like memory space from that perspective, because most of the graph queries are really, okay, they just follow exactly the pattern that you're interested in. And all the other data that's not touched by this pattern is actually not loaded. So from that perspective, there's also this use case called like knowledge graph, where you pull in data from lots of different sources and combine like your sales data with your customer data, with your analytics data, with your supplier data, where it becomes this really complex, really insightful network of information, which then it opens up a lot of possibilities and lots of new use cases. But if you decided upfront, we'll skip all this stuff, then the challenge is, of course, where do you get the information then when people start asking for it as such? So it's a balance. So sometimes you really know what your use cases are, and you can say, yes, I only want to store exactly this information. But sometimes it's more like an open-ended one, where from the business side, it's not even clear what they want to do in the future with all this, with the data. And then it's not such a big penalty, because if it's not touched and it's not loaded, then it just sits on disk basically as such.
Yeah, that makes sense. Let's focus a little bit on the read path, although you mentioned briefly. So let's assume that I have a customer and they've also placed an order. So I'm just trying to fast forward that we follow the same approach. We create relations for orders. Customer orders, let's say 2 products in one order, and they are all related now, right? There are 2 products, one order, basically line items, and then a customer. Now I want to query that, let's say, get me all the orders for this customer, for example. How would the query?
The nice thing, it basically looks exactly the same as the right part, because it's again these patterns, right? So you basically have your customer node, you find your customer by ID. So you would say customer in around parentheses and then curly braces with ID and then parameter. And then you would draw the relationship to the order. And then you would say like order. And depending if you want to fetch line items or not, you can basically also have the line item relationship and then can say, okay, from this query, please return. So what we do is in Cypher, we turn it around. So we start with the match, where what data do you want to find, then like the filtering, aggregation, and so on. And the last statement is actually in return, like in a regular programming language, right? So we don't say select upfront, but we say return at the end. So we felt that's more natural for developers, where you say, okay, this is what I want to fetch, this is what I want to filter, and this is what I return. So you basically say, and then return customer ID, order date, and so on. Or you can even return the whole order as a node, then you get a node object with all the properties on the node. And then you can also return the relationships, which then have the attributes for the line item, for instance, for quantities and prices and discounts and so on. And so basically you have the same pattern. And then from the pattern, you can say, I also want to filter, for instance, by time or by type of product or category of product or something like that. So from the read path, it's basically similar. You send the statement to the driver, gets to the server. The server has server-side routing. So it decides, do I go to basically the leader, or do I go to any follower or secondary? Neo4j has some concept called bookmarks. That's used when you want to do read your own writes, basically. So if you just did a write and you want guarantee the user that they see the write that they just did, then there's something called a bookmark, which basically is returned with the write. And then you can choose to say, I want to basically get the data where the server that I'm reading from has at least this bookmark version. Bookmark stands in for like transactions, almost like transaction IDs or something like that. So you want to say, at least this transaction should have happened on the server to return me the data. So that's an addition where you don't get eventual consistency, but you get something that's called causal consistency, where you can control the consistency guarantees as such. And then basically it goes to the whatever server is there. And then we have a query planner, of course, that takes the query, optimizes it. Can I use an index lookup for certain, like for the starting points, for instance? Do I have optimized data structures for following this relationship or other things? Is something already loaded in the page cache and so on? And then the query plan has like physical operators, and the physical operators will call kernel API functions, basically. And then, for instance, if the data is not in the page cache, then it will be loaded from disk. You have a page fault, then it's loaded from disk. Otherwise, it will be used. And then it materializes as much of the data as is needed during the query execution. And then only at the end, it fetches the additional information that you want to return. So for instance, when you want to do just a graph query across a product, but you never return the product to the user, like all the attributes of the product will not be loaded. It will only be like the ID, basically, or the existence of the product will be used. But all the stuff that you don't return to the user will actually not be loaded. And then it's basically results are streamed out. So we also have an like reactive approach as well. So you can basically also do back pressure and reactive querying if you want to. So if you don't want to do synchronous, but something like where you want to stream larger volumes of data, you can also use reactive and back pressure as such. And then it goes over the wire. So we have two options for the wire transport. One is HTTP as an API, but we have also our own binary protocol called Bolt, which is basically has its own serialization format of an like binary protocol as well. And then that's used to basically transport the data, and then the client just unpacks it and makes it available to the client program as such.
Okay.
And that's also streamed through. So as long as you don't use something like aggregations or sorting or something like that, that also, as results are produced, they are directly streamed back to the client, which is actually quite nice, because if you send larger volumes of data, then as the query is producing data, it's immediately sent to the client, so it doesn't keep server memory allocated for these kind of things as well. Yeah, that's the read part mostly.
No,
pretty
I think
straightforward.
That is straightforward, and it's somewhat similar to what happens in other distributed databases as well. Like you can choose what kind of consistency you want, and that bookmarking concept was interesting. And then it can go to any read, any follower, and then get the data.
Yeah.
And again, data locality is critical, because otherwise you will end up querying multiple nodes over network, which might be slow.
Exactly. So there's also the option, so you can also make it sticky. So basically the same types of queries go to the same reader. So for instance, the page cache is already preloaded with the data that you want. So there's also some control. So there's something like called routing policies, where you can define basically where should things be routed, for instance. So for instance, if you have a geo-distributed cluster and you want to have things, for instance, for your local, let's say European things go to the European servers and the US goes to the US servers. And so if you have like multi-data center setups and so on, so you can also control this with routing policies.
Makes sense.
And so on. So that's also... But these are more advanced use cases, of course, right? Most people don't have these complex global setups as such.
I have two more questions. So one of the problem that we face with relational database management systems is that schema migration is difficult, because with increasing feature set, you want to add new properties to your relation. So let's say to your relation table, and adding new column can be a painful thing. You have to modify a lot of things, and depending on type of column and the criticality of that column, it can be really a painful task. How is it easier in the graph database?
So what makes it easier is actually two things. So one is because the graph database in itself is schema free or schema optional. So many of the attributes are actually not predefined. So you add them as you go. So all your queries are dealing with existence of data anyway, right? So you can have users that have filled in all the fields of their user profile, and you have a lot of users where you have just the email and perhaps a name or something, right? So that means you have to deal with this dynamic style of data anyway, and then you basically default to some values as well. In general, I also recommend people not to store default values, because they just take space and can just default on them on the read path part, because if you don't need the storage, we don't need to store the stuff, right? So if it's just 0 or false or null or empty or whatever, then we don't store it, and you can default on it on the read path as such. The other thing is, because it's dynamic as such, so you can basically also do things like lazy migrations, where you can say, okay, I'm adding new data as it comes in, and then my query can actually take all the additional properties as a map or dictionary and just return them, and then the client side can use them. Or I can say, as data comes in, I can change my queries incrementally. So the query will not fail if a certain attribute doesn't exist. Like in a relation database, when you do a select something.column name, it will actually fail if the column doesn't exist, right? So in the graph database, if you do something like node.property, it will just return null if it doesn't exist, right? So it's also much more lenient from that perspective. And then if you really want to change something like a node label, and for instance, imagine I want to change it from product to item or something like that. That's of course a more involved thing, but that's something that you can also do incrementally, where you basically say, okay, I first add all the item labels to all the products, then I'm rewriting my queries and run my integration tests, and I can also do it like one by one, and because then it has two labels, product and item label as such, and then I can add like some indexes for the item label and so on. I run my integration tests, and if my integration tests are all green after, then I can start removing the product labels, for instance. So it's also something like in database refactoring, where you basically first add things and then you run your tests. You even put out a release probably with the additional added column, and when nothing breaks, then you start removing things early. That's also an option. There's also some tools, like for instance, Michael Simmons wrote a Neo4j migrations tool that allows you, if you have to really do like data migrations, for instance, if you want to change something like a data type of something, or if you want to change really more complex, where you don't just want to change like a relationship type or label, but if you have like more complex graph refactorings, if you want to say, hey, let's say line item relationship was really nice for our use case, but now we want to connect a lot of other information to this line item position. I want to also track what promotion did this come from, or what analytics information was attached to that. Then you can basically evolve the relationship to a node, and then it turns into a node and has two relationships. But if you want to have these more complex database migrations, then there are toolings like, one is called Neo4j migrations, and then the other one from Florent is a Neo4j integration for Liquid Graph, for Liquibase, where you can also use Liquibase with Neo4j as a migration tool as well. But it's much more rarely needed because of the inherently flexible and dynamic structure that's underneath the database, and because the queries don't break if you just add or remove a column, then you basically either get just null back, or if you remove the really critical column, then you might get no results, but it will not break your system immediately as such. And then, so from that perspective, that's probably a little bit like dynamic typing and static typing in some way. And if you use frameworks like object graph mappers, like for instance, like Spring Data Neo4j or Neo4j OGM or similar ones, Neo model for Python, then the object mapper does the work basically of translating your model into queries anyway. So that means when you make the change in the object model, then all your queries are already adjusted, and then you basically just run the background migration in the database like you would do otherwise as well. So where then basically the application controls more the shape of data that goes in and out of the database, right? And then it's basically on the application side when you want to make refactorings on the application domain model, then this would propagate into queries automatically. And some of these frameworks even have the ability to generate migration scripts out of the box. Also that changes, for instance, something like property names or property types or things like that as well.
Cool. Yeah, I think that makes sense. Talking a little bit on the use case, right? So companies, they have been using relational modeling even for graph type of nodes and objects and whatnot. And they have workarounds. And the companies that typically end up moving to a graph database, something like Neo4j, what is their typical persistence layer? Do they believe in polyglot persistence where they say, okay, I'm going to still have my relational database for still all the other queries, but when I want to query more relational type of queries where, again, I say relational, but I meant relations more between these two, graph-based queries, I'll use graph database. So is it like they keep both, or is it like they just replace and completely give away relational databases?
Yeah. So in most cases, of course, they keep their relational database, right? So because the relational database is a system of record and it serves a lot of existing use cases already. So I think you can almost see it like if someone adds Elasticsearch to the application, right? So where you basically say, hey, I want to provide this new use case, like for instance, pathfinding or recommendations, or I want to manage complex organizational hierarchies, or I have a referral scheme that I need to basically compute, or I have a complex, like for instance, aircraft manufacturers that have million-part bombs, like bill of materials as such, right? Which is massive tree, right? On the top is the aircraft, and in the end, it's a little screw, and then you have many layers between them, right? So if you want to manage this, then of course your source data, like from your manufacturing system, can still be in the relation database. But if you want to basically do the graph use cases, for instance, which groups of parts need to be placed or something like that, then you would use a graph database for these use cases, right? And then you add Neo4j as a system, and then you integrate with your existing database using CDC or Kafka or some other approach of data synchronization. And then you build your services or microservices that would use the graph database, and then you add it there. You have some cases where people use pure Neo4j, but that's more like on the startup side, when you have a startup that's using something like, either a social network or something that has a knowledge graph or supply chain use case, for instance, where the whole use case is basically a graph use case. Or if you have like logistics and routing use case, where it doesn't make sense to store the data in any other way, then you would basically use a full graph database. And that's oftentimes the case when you have someone starting out, or if there's a new department for something like that. And sometimes we also see with existing customers that they start small with one use case. For instance, let's say a pharmaceutical company that does drug discovery or something, or drug repurposing, right? They start with this very special use case of drug repurposing, but then they notice, we can use this graph database to store all the genes and diseases and drugs and clinical studies and all this stuff. Now we suddenly have a knowledge graph of all our whole company, basically. Let's see what all these other cool things we can do. So sometimes it starts really small as a small use case, and then it grows pretty big inside that company. But because they have still all the existing manufacturing systems and so on that run on Relational, so they integrate Neo4j with their systems. But for most of the large companies, it's like opening up additional use cases as such. And then it's a polyglot architecture where you either use something like an event-based system or some other kind of data application that then syncs the graph, or you use microservices where you basically say, this is my recommendation service, or this is my pathfinding service, or stuff like that. And then that gets like with CQRS also filled with domain events, for instance, as well. And then you have read. Then it's more like read view. But for some of our customers, Neo4j also became basically the system of record. And then they moved out of, like I mentioned for Adobe, like out of Cassandra or Mongo, and then replaced it completely with Neo4j because it was a social network in the end. So it was basically a graph use case. After all, it just took them some journey to get there.
Makes sense. So it's more of a use case migration and not like the entire database would migrate. That makes sense. I wish we had more time because I feel like we are just getting started.
Happy to
But
come back at some point.
exactly. So
yeah.
we should do this again. But Michael, thanks a lot. This was really insightful. And
you.
I have a
Yeah.
better understanding
great.
of relational databases versus graph databases and what they are. So thanks a lot for
Yeah.
sharing the insights, and we should do this again on some other
Great
topics.
questions. Yes. Let's do that. Thank you.
Thank
Have
you.
a great day, everyone, and take care.